first speaker is Roman. He's going to talk about extending Kubernetes. And he will start soon. After.
So, thank you for the introduction. Glad to see that so many people joined. My name is Roman. I'm working for Red Hat as a software engineer. And I want to talk to you today a little bit about declarative and imperative systems, and especially how in Kubernetes you can create declarative extensions to Kubernetes itself with your own types. When we look about the content first, I want to talk with you a little bit about imperative interactions with software. After we're through with that, I want to actually show you the same flow we're going through with the imperative flow, how it can look like in a declarative flow. Then I want to tell you how Kubernetes in general creates control which can look into such declarative systems, and then we'll have a look at the main structs that's a little more order related, which Kubernetes uses to create clusters composers. And the main structure are the so-called list box, the concept, the store, the shared informant, the workqueue. So let's start with the imperative interactions with software. I may have a little example that I want to go through with you, and that's, let's suppose we have a virtual machine management application, and we have a pretty simple task to do. We just want to create a virtual machine and disk, and that can't be that hard, right? We have a little state machine, where you can see all of the steps you can go through. First, we have no disk and no virtual machine in the system. So the first thing you do is you call the REST API and create a disk. Once you created the disk, normally you have an asynchronous process going on in these systems, which is actually provisioning the disk for you. So it's not immediately available. So you are waiting a little bit for it to show up. Then you create a virtual machine. Now you can actually create it because it exists. Many systems don't even allow you to create a machine before the disk exists, which is referencing. And finally, we can start the virtual machine. So far, so good. Let's now introduce the person which has to do that work, and that's the user. So the user has in its head the final state of what she wants to achieve, but can't tell the system what it wants to do. Instead of that, it has to go through all these processes I've already told you, and then mark them in red here. So the user first creates the disk, then the user waits for the disk to show up, then the user creates the VM, and then the user starts the VM. I guess in the head of many of the people there are already threw up some bash scripts which would do that or whatever. And at first, yeah, it's not very nice, but still you just have the REST calls and everything is there. But when we look into more detail, we have to do more. We have to add retry logic. We have to, for instance, if we can't connect to the cluster, we have to make sure that if we can't connect to the cluster, that we don't overload the cluster by just quickly doing REST calls again. You probably have some backup mechanism in there, so your back script or your application grows and grows. And all that work you do there does not at all immediately tell other people what's the final state, what's the final state you want to reach. So you can start thinking about how you can actually start expressing the state you want to reach. And with imperative systems, you can use, for instance, Ansible to help you there. So you can create an Ansible role, put all the tasks you have to do there. It already has some helpers for doing all the retry logic and so on. And then you can assign a specific, and so you can put your mind, the state in your mind, the final state, into an Ansible role. And the user then just does something like this: Ansible role, Python 2 role on the host localhost. This would just, with other words, I want Python on my node, and I don't care how it gets there. Someone else can write the role. So that's declarative thinking. So that already goes into that direction of declarative systems, but the system itself is declarative. Now we can look at the same example on how it would look like if the system itself would be declarative. And therefore, we have to introduce an operator, and the operator is actually the system which performs the steps for the user. So the user now has the final state of what he wants to reach, not only in mind, can really express it and can, for instance, store it in Git, and everyone can more or less easily understand what the final state is of the user's mind. And with the operator, who does all the work for the user. Here you again you see the user, and in the red circle you see what the user now has to do in the system. He just posts the state of what he wants from the system, and he doesn't care about all the intermediate states. And here is an example of how such states can be expressed in Kubernetes. I'm working on Kubernetes. That's an extension for Kubernetes which allows you to manage virtual machines. And we were creating a virtual machine extension to Kubernetes, and here you see a description of the virtual machine. As you see behind it's a virtual machine object, it's here. You can specify how much memory it has, you can attach a disk to the virtual machine, and reference the persistent volume claim, which is the empty disk we want. And then you can just create an ordinary persistence volume claim in the typical Kubernetes YAML format, and in this case we want a disk with 8 GB. And you post those two YAMLs to the cluster, and then the operator starts doing all the work for you. It fetches the YAMLs, it creates the disks, waits for the disks to be there, creates the again, starts again. Much easier for the user. But now we engineers have to deal with the complexity. So it's not going away, it's just somewhere else. And that brings me finally to the part where we can talk about how Kubernetes solves that problem. And Kubernetes has some basic considerations when it comes to writing controllers. One is we have a cluster state, and we are trying to follow that cluster state. So Kubernetes is not trying to, but we're not following every state of the cluster. We're just trying to converge to the final state we want to reach. So, I don't know, you get virtual machine update events, you see you have to react on them, and you just try to adapt the cluster to it, but you don't guarantee that you are going through every mutation of the object. It's just, you guarantee at the end you will reach the desired state. And this has advantages when you think about how Kubernetes controllers store the state, react on the state of the cluster, because they have an in-memory view, a cache view of the cluster, and they can and with that consideration that you don't have to process every state, they can have some very nice simplifications to reach the final state. The first thing you have to do when you want to create controllers in Kubernetes is you need access to the data and create your in-memory view. And the first construct I have here is a so-called list watcher. And that's an actually very simple construct. Here you see the interface definition go. You have two methods on it. First, a list call, which just does a REST call and lists all available resources for the pods. And then you have a watch call. So after you've listed all pods, you start watching for changes in the pods. Kubernetes has a very nice watch API where it just opens a WebSocket and you get all the updates of the pods. And since it uses XCT in the back, it can leverage the XCT's resource version function, or the function resource version field. Whenever you mutate an object in the XCT cluster, it gets a specific resource version, and you can start watching directories based on a specific resource version. That's what the watch function reuses. And when we look at an implementation of such a list watcher, the result is therefore pretty simple. You see here a function which creates a new list for open client. First, we create a list function which needs to return. We can, oh yeah, that's something that you mentioned. I'm talking here, all those constructs are not just internally used by Kubernetes. Kubernetes guys really made a great work of creating an extra Go SDK, which is directly synchronized out of the core repository. All code snippets you see here are using core code from Kubernetes, but through the Kubernetes SDK. So you can just fetch the SDK and write your controllers the same way like core Kubernetes contributors are doing. And here you see the result of it. I'm just using a default REST line from the Kubernetes core repo here. build a REST path and fetch all resources from the endpoint. And for the watch functionality, I'm doing pretty much the same. I am creating the right REST path, creating a watch metrics, I specify namespaces to look for, I specify resources that can be pods, virtual machines, or whatever the extension is. Add some extra parameters, you know, that you care about them, actually just add them. You can specify field selectors, so that helps you to say my controllers really just care about a specific label pods, not all pods in the cluster. And you start watching. And then that's it, you just return it. And you have a list watcher, which lists and watches and emits update or delete events for your object. That's the first step. Now one could already think, hey, now I get all the events coming in from my controller. Why not just take that event channel I get from Go and do my business logic now based on those events? And that's not a very good idea. First of all, controllers can have more than one resource. Then it's hard to combine all the events properly, because you get from resource A an event for object X, and from resource B you get an event for object Y, and you don't really have a place to correlate them, to look at them together. Second thing is, the list watchers don't provide any retry mechanisms or anything. So they're really just good at one thing, but they're very good about emitting events of changes in the cluster and showing you which resources are there in the cluster. The next thing here to get started with creating a full controller is introducing a store. Stores can now help you by taking the events from the list watchers from different sources and fill different stores with the objects which are muted by the list watcher. And now you have a place to store your in-memory view of your cluster. A store is a single write amount of a reader construct in Kubernetes. Internally, it's mostly simple memory-based map. And you have a few simple methods on how to add stuff and how to access stuff. Basically, you can add, update, or delete objects in this case. They are entered to the store. And then I have a few different ways of getting the objects out. One is, for instance, get by key. Typically, key in Kubernetes consists of the name of the object and the namespace it is in. So here, I'm trying to get the pod called pod1 in the default namespace, and I get the object out of that directory. It's very open, it's other methods like list listable content of the cache. And here we can see the full interface it implements add, update, delete, so it's simple list to get all the object, list piece to just get the objects which are in, get to check if an object is in the cache, which I already have, or get my key to get it. Pretty simple. And now we're already a little bit farther. Now we can fetch the state from the cluster. Now we can fetch resource changes from the cluster to list watcher, and we can use the store to create an in-memory view of the cluster. And Kubernetes helps us even farther. Now they introduce the shared index informer, which takes the list watcher and the store and makes sure that the list watcher updates the store for you. And it allows you to register callbacks. And these callbacks are also very simple. It's add, update, delete callbacks. And whenever an event is coming in from the list watcher, it will try to call you callbacks. Censorship, here is a very interesting side note. A shared informer does not guarantee that when an event is coming in and your callbacks are triggered, that you are, here I probably better show you this picture where you can see the delete update signatures. So when a list watcher updates the store and the shared informer then invokes the callbacks, it will, for instance, call you add method if an object was added, and it will provide you with the object, which was triggering the update. But the interesting side note here is that you're not guaranteed to see the object state which was coming in by the list watcher and which was triggering your callback. Maybe I'll try to explain once again to make sure that you guys really get it. It's not that hard, but a little bit hard to express. So there can be 2 or 3 very fast updates on the same object, and you can have many callbacks on the shared informer. So it can be that a part of the callbacks were invoked after the first update of the object was coming in. In the meantime, 2 new updates are coming in for the same object, and the cache is updated, but the callbacks were not even invoked for the first event yet. So what the shared informer then does is providing the latest state from the cache to the object. And that's a very neat idea to reuse the shared informer for as many callbacks as possible without having that overhead of tracking all the different states parallel. And you can still reach the goal of reaching the final state which you want, although you're not processing every object mutation. Here is an example of how such callbacks can be implemented for a shared informer. And we just create a resource in an handler function struct, add an add function, after function, each function, and in there you can take the object and operate on it. Again, now you might think, hey, now we're there, right? We have the shared informer with the callbacks, we have the store, the in-memory view. Now we can put our business logic in here, in this update and delete functions. But no, not a good idea. First of all, the shared informer involves locks, and there is something very interesting with code internally. If you are locking if the Go routine locks for a very long time, and for instance, business logic normally takes a lot of time, and you have the same Go routine already trying to acquire the lock immediately afterwards again, the other Go routine, which acquires the lock just for a very short amount of time, doesn't get the lock. So you would end up with reprocessing over and over the callback code, but never updating your cache, which also needs the lock. And that's, therefore, these callbacks need to be very short because of the code limitation or Go architectural decisions. I don't want to judge that. And the second, and the next thing is, as you can see, the callbacks here, they just take an object but return nothing. So there is again no place to do error handling here in the same way. No retry mechanism or anything. But what you can do now here is you can use the callbacks to enqueue the key of the object which changed to a work queue. And the work queue is the final missing piece, which will help us. A work queue at first glance looks like a completely typical queue implementation. You get something, you have an object in, you get something out, you get the object out. The same order like first in, first out order. But it has a few optimizations which make writing controls very convenient. The first one is, and I'll show you details after I went through the list process cases, if you get multiple updates for the same object, they're all collapsed into one edit key, so you don't end up processing every mutation. It just collapses all the keys so you don't have to process, so you don't wake up the queue 5 times because it's just not necessary. The work queue internally knows when a key is processed on it when you're done with processing, and that allows the work queue to make sure that you don't have to care about locking on keys so that you don't process the same key or the same object in parallel in different workers. The queue does that for you. It allows mechanisms to re-enqueue the key you're currently processing in case of errors. It even allows you to specify retry policies and backup policies, and that is why it also has a history of re-enqueuing in case of errors. If we now go through the list in more detail, first the thing where it looks like a normal map. You have your queue, it contains a cube system pod 2 pod and a default pod 1 pod. And you want to add a default pod 2 pod key. And the result is like expected to call add, and it's just added in the back of the queue. And you have 3 keys in there now. But you already see the difference when you already have a key in the queue and you try to add the same key again. Then that's perfectly valid. But the result will still just contain 2 keys. So you can enqueue a key just once, and that's all you need because you don't. Since you have a cache with the latest in-memory view of the cluster, you can't even process every object mutation. So you're just interested in detecting, okay, it has changed, and I need to process it. And if I didn't yet process it, it's good enough to just have it marked as I need to process it. I don't need to mark it as process it 5 times. It doesn't mean I see 5 different cache changes anyway. And the queue also makes sure for you that you don't have to care about processing the same key in parallel multiple times. That could lead to strange race confusions. Just consider you have a replica set which should create 5 pods. And you have 2 updates on the replica set for creating the pods, so it's in queue 2 times. And you DQ it first, and then DQ it in another work again. So both are trying to work on these changes, and both are trying to create 5 pods for you. At the end, you have 10 pods, and then over time, they probably adjust and start deleting them again, and at the end, you end with 5. But you would have to take care yourself about all the blocking work you have to do by tracking which keys you got from the queue. So when you do a get on default, when you do a get and you get the default for 1 key out, and you add the default for 1 key again and do another get in another workbench, you get nothing out of the queue, although there is something in the queue. Only if you are done with processing and call done on the queue with the key, another get would give you the object. And now we get to the very important error handling capabilities. If you are getting a key out of the queue and you're processing it and you have errors, you want to reprocess it. But normally you don't want to immediately reprocess it, or maybe the first time you want to immediately reprocess it, but not if it fails 5 times. Oh, and yeah, it should be doing 5 minutes. So what you want to do, you want to add the key rate limit so that it doesn't immediately get out again. And here you see it. So we are processing the event. We have an error, but we're processing the key. We have an error, and we add it rate limited again. It gets enqueued again into the queue, and when I immediately do a get afterwards, it gives me nothing out. Only after a specific delay, which can be an exponential backup or whatever, for every rate limited call, you get the object out again. That's the very same pattern, not over the cluster. And there is then a final configuration which you need to take into account, and that is the queue internal also tracks the failure history. So if you called 5 times at rate limited for the same key for the 5 times, then the queue internally tracks 5 times error, and that's important, for instance, to calculate a backup. And when you then finally manage to do a successful processing of that key, you have to do an extra forget call for that key to make sure that this error history gets decoded and it gets normally edited in the okay, you just take a working interface, it contains all the methods we were talking about before. And now we're at the end pretty much, because now with all those components we can create a controller. And the controller uses the list watcher and the informer and the store provided in clusters in-memory view. It uses the callbacks of the informer to add the keys to the work queues. The controller has worker loops running which use get to DQ keys from the queue. If there are errors, it uses add rate limited to add the key again for later processing. On success, you have to make sure that you forget error history if you had one, and you have to call done so that other workers can work on the key again. And here we have a nice picture which does that too, which illustrates it too. On the left side, you see the shared informer again, the store internally, the callback of the informer into the work queue. Here you have the controller coroutines. They are using the block get calls to get the keys out of the work queue, and based on the key they fetch objects from the stores from the informer. Now they have everything, they have access to the objects and to the key they want to process, and they can react to changing the cluster with doing extra rest calls by creating pods or whatever. And depending if something was a success or an error, they can call the right calls in the work queue afterwards. Like these calls are done, forget, at rate limited, at delay, or stuff like that. And I don't know how much time left. 3 minutes? Okay, then it's perfect to go with the do's and don'ts again, which we collected during the talk. And so here, the list watchers are really just there for updating stores. Don't even try to react to the events they're providing directly. There's just no code out there in Kubernetes to proper project error and error. Use stores to get the latest state of the node object, and don't try to manipulate the cache directly. Let shared informers do that for you. It's a read only. It's a single reader multiple read, a single writer multiple read implementation. And you don't even have access to the logs, so don't try to do that. Then copy objects from the store before you try to manipulate them. When you get an object from the store, you just get a reference to the object in the cache. So if you're directly, for instance, taking a pod out, manipulating it, and want to update it on the cluster, you're also manipulating your cache. But the cache should be updated based on the state of the cluster and not based on your mutation directly. So you first need to decopy. Kubernetes has some performance generated decopy functions for that. And when you use shared informers, don't use the callbacks for doing your business logic. Just use them for notify work queues about changes. And finally, that's a very interesting one. In Kubernetes, you normally have the object with the specification and the status in one place. So don't try, when you, for instance, have a pod, a replica set which should create 5 pods, don't try to implement it the way that you say, okay, now I created 5 pods, so I immediately also update my status to have 5 pods and push it. What you will see is that your pod count will start to go up and down pretty much randomly, because the in-memory view of the cluster did not yet recognize that you have created the pods, and it does not yet know that there are 5 new pods. Maybe just sees 3 pods in the next update, because the next creation events didn't even reach it yet. So your status will just behave very strange. And yeah, that's pretty much it. Here are links for interested people to see actual implementations and how Kubernetes and Kubernetes guide. And there is even more, but it's just not the full time. For instance, reference management, managing of objects, talking about garbage collection and all that stuff. Also, yeah, a lot of more stuff. Okay, thank you.
So if you want to leave now, you need to be very quietly